Assuming there is an atom with single electron and k discrete energy levels, according to superposition principle, we can denote the state of the electron as the superposition of all the k energy levels with their corresponding complex amplitudes. The state of the electron must be normalized, which means the sum of the squares of the amplitudes should be equal to 1. Assuming we have an atom with single electron and we somehow manage to confine the energy of the electron up to the first excited state and not beyond that, then we can write the ground state as 0 and the first excited state as 1. According to superposition principle, we can write the state of the electron as alpha 0 plus beta 1, where alpha and beta are some complex numbers. And this state is normalized, which means alpha square plus beta square is always equals to 1. We can actually denote the state of the electron in vector form, where alpha and beta belongs to the complex vector space, and this is the ground state and this is the excited state in a unit circle, because the length of the state is always 1. If we measure the state, then we end up getting either one of the state, either 0 or 1. If we end up getting a 0, then the new state would be 0 with probability alpha square, and if we end up getting 1, then new state would be 1 with probability beta square. Actually, we are destroying the state by measuring it. So if we measure the state, we are destroying it and we end up getting one of the basis vector. If we're having two qubits, we actually take the tensor product of the first qubit with the second qubit. Let's assume the first qubit electron state is alpha naught 0 plus beta naught 1, and the second qubit's electron state is alpha 1 0 plus beta 1 1. We actually take a tensor product of both qubits and we get the corresponding 4 states, and the state of this qubit combined is a superposition of all the 4 states. As you can see here, alpha 0 0, alpha 0 1, alpha 1 0, alpha 1 1. And if we measure the alpha, then the state of the qubit would end up in one of the 4 states. What if we only measure the first qubit? If we measure the first qubit and we get a 0, then we actually need to cut out all the other states which are irrelevant to the answer, and we just need to normalize the new state which has the first qubit as 0. We can measure the state of the electron not only in standard 0-1 basis but also in any other orthonormal basis in the unit circle. Here, plus and minus are orthonormal bases, making a 45-degree with the standard 0-1 basis. We can write the plus and minus bases as the superposition of 0-1 bases like this. As I have told you that if there are two qubits, we have to take a tensor product of the first qubit with the second qubit to get all the 4 possible states, and the new state would look something like this. If we factor this state, we get back the states of the first qubit and the second qubit. But there are some states which cannot be factored out, and those are called the Bell states. It is as if the first qubit is entangled with the second qubit. We can actually take an example of two electrons in a covalent bond which are entangled with each other. If we measure the Bell state in any other orthonormal state like UU perp or in the sign plus minus basis or the standard 1-0 basis, we actually end up getting a Bell state only. There's something interesting about entanglement. If we have two qubits entangled with each other, and if we put the first qubit on Earth and second qubit on Moon and measure the first qubit on Earth and end up getting a 0 with a probability of half, the new state would be 0 0. And now if we measure the second qubit on Moon after we have already measured the first qubit on Earth and got a 0, then the new state of the second qubit would be 0 with probability of 1, and that's the power of entanglement. Quantum gates tells us about the evolution of quantum state in time. Since we can represent the quantum state in complex vector space or Hilbert space, we use unitary transform to rotate the Hilbert space. Every angle is preserved in Hilbert space. Bit flip, denoted by x, flips the bit of the qubit. It maps 0 to 1 and 1 to 0. If bit flip gate acts on a qubit which is in a superposition of 0 and 1, it flips the bits of the qubit. Here alpha 00 plus alpha 11 is mapped to alpha 10 plus alpha 01. Phase flip gate, denoted by Z, flips the phase of the qubit. It maps 0 to 0, 1 to minus 1. It maps plus to minus and minus to plus. Phase flip gate, when acted on a qubit which is in superposition of 0 and 1, flips the phase of the qubit. Here alpha 00 plus alpha 11 is mapped to alpha 00 minus alpha 11. Hadamard gate is also a unitary transform. It maps 0 to plus and 1 to minus. Here plus and minus are orthonormal bases making a 45-degree with the standard 0,1 basis. We use Hadamard gate to create a superposition of standard 0,1 bases. The C0 gate is a 2-qubit gate and its matrix representation is something like this. The C0 gate actually is denoted like this, and the first bit is called the control bit and the second bit is called the target bit. If the control bit is 0, the target bit is unchanged. If the control bit is 1, then the target bit is flipped. As you can see here, the control bit is 0, the target bit is unchanged. But if the control bit is 1, then the target bit is flipped. If it's a 0, then it has become 1. If it's a 1, then it has become 0. We can create a Bell state with this simple circuit. Let's initialize the 2 qubits to 0 and apply a Hadamard gate on the first qubit to get the superposition of 0 and 1. Now we take a tensor product of the first and the second qubit and end up getting a state something like this: 1 by root 2 0 0 plus 1 by root 2 1 0. Now we apply a C0 gate on this state and get a Bell state. As you can see, since the control bit is 0 here, the target bit is not changed. Since the control bit is 1 here, the target bit is flipped to 1. Let's suppose Alice and Bob are miles apart. Okay, let's put Alice on Earth and Bob on Martian surface using SpaceX capsule. Alice actually creates a state psi out of her qubit. She's so excited to share the entire state psi with Bob, but she doesn't know how to. If she measures her state psi, then she destroys the entire state. As I have told you, measurement projects the state psi onto one of the bases, 0 or 1. So if she measures the state psi and ends up getting 0, then the new state would be 0 with probability alpha square. And if Alice measures the state psi and ends up getting a state 1, then new state would be 1 with probability beta square. So by measuring, she has destroyed the entire state. Bob wouldn't know the entire state if she measures this. So how can Alice teleport psi to Bob? She actually uses the Bell state, which is shared between Alice and Bob, to teleport the entire psi state with Bob. So let's assuming this part to be the Alice's lab on the Earth and this part to be lab of Bob on the Mars. So this first wire is Alice's qubit wire, the second wire is the Alice's Bell state shared qubit wire, And this third wire is the Bob's Bell state qubit wire. So Alice and Bob are actually sharing a Bell state with each other, which is 1 by root 2 0 0 plus 1 by root 2 1 1. This is the entire circuit which is used to teleport Alice's qubit state psi with the Bob. So first we actually take the tensor product of the Alice's state psi with the Bell state she shares with the Bob. So we actually take a tensor product here. As you can see, this is the Alice's qubit state, and in the Bell state, the first qubit is the Alice's share of the Bell state qubit, and the second qubit is the Bob's share of Bell state qubit. So we take a tensor product and we end up with a new state like this, which is alpha by root 2 0 0 0 plus beta by root 2 1 0 0 plus alpha by root 2 0 1 1 plus beta by root 2 1 1 1. So the first qubit is Alice's qubit. The second qubit is the Alice's share of Bell's state qubit. The third qubit is Bob's share of Bell state qubit. Now we actually apply the C0 gate on the Alice's state, which is the first qubit of this entire state, with the Alice's share of the Bell state qubit, which is the second qubit. So as you can see, if we apply a C0 gate here, then since this first qubit is 0, the second qubit has not been changed. If the first qubit is 1, the second qubit has been flipped from 0 to 1. Here the first qubit is 0, so the second qubit is untouched. Here the first qubit is 1, so the second qubit is flipped from 1 to 0. In this circuit, this is the measuring device and this is the Hadamard gate, and these two lines are just the wires connecting Alice and Bob, like a telephonic wire or a satellite or something just like that. So if we apply a C0 gate on the first and the second qubit, we end up in a state something like this. So the middle qubit is the Alice share of the Bell state qubit. So Alice now measures her share of Bell state, and if it turns out to be 0, then the new state of the first and the third qubit would be alpha 0 0 plus beta 1 1. Here this is the first qubit, this is the third qubit, here as well. And if it turns out to be a 1, then the state of the first and the third qubit would be alpha 0 1 plus beta 1 0. Here this is the first qubit, this is the third qubit. So now Alice calls and tells her result. If it's a 0, then Bob applies nothing on his share of qubit. But if it's a 1, then Bob applies a bit flip gate on his share of qubit. As you can see, if he applies a bit flip gate, then a 1 and 0 would flip. So the new state would be alpha 0 0 beta 1 1, which is shared with the Alice. Now if Alice measures her qubit and if it turns out to be 0, then if Bob measures his qubit, then it would be a 0 as well. And Alice did not share her psi state, it is just a part of the psi state. So what would Alice do is, she actually measures her state of qubit in sine basis. So if we convert the Alice's qubit into sine basis, so 0 would be 1 by root 2 plus 1 by root 2 minus, and the tensor with the Bob's qubit here plus the 1 of the Alice's qubit would be 1 by root 2 plus minus 1 by root 2 minus and the tensor with the Bob's qubit, and we end up in a state something like this, where the first qubit is the Alice's qubit, which is in sine basis. So now Alice measures her qubit and if it is a plus, then she calls and tells the result to Bob. Now Bob measures his qubit, and as you can see, it turns out to be a psi state, alpha 0 plus beta 1, which was actually created in the Alice's lab, which she actually wants to share with the Bob, and she has successfully shared the psi state with Bob without destroying it. And if the measurement of Alice on her qubit turns out to be a minus, then she calls and tells the result to Bob that it's a minus, and Bob now applies a phase flip gate to his share of qubit, and this state actually converts into the psi state. Surprisingly, Alice has shared the state psi with Bob, and that's the teleportation.